Now, problem 17 on 8.4, we start out with what looks like a fairly simple looking integral. And in the instructions, it does say use a theorem. Well, we'll take a look at where this theorem or this formula comes from as we work through this. But we'll be going through trig substitution, and at some point we'll run into needing to use integration by parts. And this is what has stumped a few of you and given some problems. So let's take a look at, first off, in trig substitution, we would let let x, we're not doing u substitution now, we're doing x substitution. Let x be what? With this in here, and especially with the 16 and the 9, we need x to be 3/4 times tangent theta. Okay. The 3/4, when we square 3/4, we'll get 9/16. The 16s will cancel out, and then we'll be able to factor the 9 out. And then the tangent is needed. We'll have 1 plus tangent squared theta, which is your secant squared for your identity. Now, we still need to look at what dx is before we start plugging things in. Well, other direction, derivative of tangent theta would be secant squared theta. So when we plug all this back in, well, like I said, the inside, we'll go through real quickly what I talked about. 3/4 tangent squared, 3/4 tangent theta quantity squared would give us the 9/16 tangent squared theta, and then dx being the 3/4 secant squared theta d theta. And like I said, this simplifies. We can factor out a 9, and we'd have 1 plus tangent squared theta under the radical, which would give us square root of 9 times square root of secant squared theta. And so all together, this whole thing, simplifying this, we would end up with 3 times 3/4, or a 9/4, times the integral of secant theta times another secant squared theta, which would give us secant cubed theta, and then the d theta. So by doing this trig substitution, this whole thing turns into this. Questions so far? Now, this is where we're going to shift gears a little bit and look just at this secant cubed theta. Then we'll kind of get it back into this particular problem. But we'll take a look at it in terms of secant cubed x dx, and then we'll come back and plug it back into the theta stuff and go back to problem 17. But this secant cubed x dx, this antiderivative requires integration by parts, and then it's kind of a repeated integration by parts that we do a tricky little thing of solving the equation. I think Professor Berger talked about that a little bit back in the integration by parts section, but it's definitely something that's not real obvious, and it's pretty easy to mess up. So let's go through this. In this particular case, let's let u equal secant theta, and dv, we'd be left with secant squared. Well, I'm using x. Let's use x instead of theta. Okay, so as we go through integration by parts, du would be secant x tangent x dx, and v will equal what? Okay, just the tangent x. So our integration by parts then, separating secant cubed into the secant x times secant squared x, we can then do u times v minus the integral of v du. Okay. And then manipulating this, well, there's not a direct way to integrate that part. What we can look at, I guess again we'll write down what we have and then rewrite. We would have secant x times tangent squared x dx, and we're going to change tangent squared x into its identity. What is it? Secant squared x minus 1. Okay. So multiplying this secant x through those parentheses, we get a secant cubed x again, and then minus secant x. And once again, this is just one small part of the big problem we started with on the trig sub. No wonder they said use the formula. But we're developing that formula and seeing why that formula works. But with this one, we'll now have secant x tangent x minus, now here I'm going to separate this into two parts. So I'll have minus the integral of secant cubed x dx, and then minus this negative would turn this into a plus integral of secant x dx. Now there's also a nice little formula for integral of secant x. I'll go ahead and show you how we get that formula as well, and then we'll take a look at the formula, the table of integrals, and you can see where at least some of these formulas come from. But we've got integral of secant cubed x dx is where we started, and that's equal to all of this. I'll have to write a little smaller to get all that in there. I guess it does fit. Okay, so a couple more details here. First of all, let's go ahead and look at what this, how we do this. And there's an algebra trick that I don't think too many of us would be able just to come up with this on our own, but I'll show you. Somebody came up with the brilliant idea of multiplying secant x, or secant x over 1, by the fraction secant x plus tangent x over itself. So now, well, let's go ahead and multiply secant x through the top. And this looks like a much more complicated integral, but it actually fits into something we could do. Let's look at this in terms of substitution. What do we usually look for in substitution? When we have a fraction, we let u equal the bottom part. And that's going to be very nice for us in this case, because du turns out to be what? That's a square. And then times the dx. Well, where do we find that in our integral? That's the numerator. Of course, opposite order, but adding is commutative. So really, we just have du over u, or 1 over u du, which by now, I hope this is automatic. Natural log of the absolute value of u, which u, again, was our secant x plus tangent x. So the natural log of secant x plus tangent x. Now, remember back at the beginning, that was our integral of secant x dx. And we've shown now that that's going to equal this nice little, well, nice big natural log. That's where that comes from. And on the table of integrals from the Thinkwell material, that is actually number 13. So this right here, we can automatically now just use the table of integrals, turn that into natural log of secant x plus tangent x. Or in the case of problem 17, secant theta tangent theta. Okay. Well, we still haven't gotten to the really confusing part. We're trying ultimately to integrate secant cubed x. And, well, what we need to think about here, this shows up another time on the right side of the equation. And I think what Professor Berger does is he says, let this be a certain value, I, okay, so plug I in for that. Well, that would be I as well. Watch your coefficients though. We'd have a minus I on the right side. So let's go ahead and rewrite this, I guess top of the next page, but putting in I for these two parts. And we'll go ahead and put in our formula here for integral of secant x, if I can remember all that. So we'd have I equals secant x tangent x minus, in the integral of secant cubed x, which we're calling I, and then plus the integral of secant x dx, which we found was this. And of course, somewhere along the line we're going to put in the plus c We've got that constant after integration. Well, we actually turn this into an algebraic problem. We need to solve this equation for I. Well, we've got an I over here, and we've got a minus I on this side. What do we need to do to solve that for I?
Just add it over.
Okay. Add I to both sides, and the left side will have 2I. And the right side will have secant x tangent x plus our natural log. Plus the c. And then finally, to show what the integral of secant cubed x dx is, to show what I is, we've got to divide both sides by 2, or multiply by 1/2. In this case, multiplying by 1/2 is a little bit easier. And we'll go back to this form. 1/2 times each part. Now, 1/2 times c is still just a constant, so we can leave that as c. Or we could call it 1/2 c if you want, but it's still just some constant. So that is how some of these formulas are developed on this table. And that right there turns out to be number 35 on your integral tables. Top of the second page. That's where we get how we get those parts for the secant cubed x. Now, at this point, since we've already went through the integration by parts, and now we're dealing with trig substitution, rather than going back and proving this formula, let's just go ahead and use this formula here for problem 17. And that'll make life a lot easier. And so from then on, you can go back and do your trig substitution and work through that. But that's the formula that they're talking about on number 17. Okay? I think we'll stop with that one and let you guys finish out the trig sub part. Any questions?